In the last lecture, we really left off with the energy balance for a closed system. And that was that the change in the internal energy of the closed system was equal to the amount of heat transferred between the system and the surroundings, plus the work, either the work done by the system on the surroundings or the work done by the surroundings onto the system. So what I'd like to do today is to solve 3 example problems where we directly apply this equation. And you will remember that we said last time that delta U was the integral of CV dt, or n times the integral of CV dt from T1 to T2. I'm also going to talk a little bit about the origins of that. So we're going to actually derive an expression for the constant volume heat capacity for a monatomic ideal gas, you know, something like argon, right? 1 atom. All right. But first, I want to pick on this equation a little bit, and I want to do so in a way where we don't have to worry a lot, that we don't necessarily have to worry a lot about, you know, gases and that kind of stuff. So we'll look at other types of work. And my favorite other type of work is electrical work, or you'll see in the second example problem that we'll actually treat something like that as heat, and then we'll talk about that a little bit as well. So let me bring up our first problem that we're going to look at today. And I don't know about you guys, but this is something that's actually happened to me more than once with my computer. So we're going to say that we have a laptop that has a battery that's rated at 11.1 volts and 56 watt hours, and it's placed inside of an insulated briefcase and the battery's fully charged. But I've had this happen to me where I close my laptop, I put it in the bag, I assume it went to sleep, I go to pull it out later, and it's really, really hot, and the battery's totally dead, right? So in real life, my briefcase is not perfectly well insulated, but this problem kind of asks us, if it were, how hot would the laptop get? Right? So it asks us, if no heat leaves the briefcase, the heat capacity of the briefcase is negligible, and the laptop has a mass of 2.3 kilograms and an average specific heat of 0.8 kilojoules per kilogram degree C, estimate the temperature of the laptop after the battery has been fully discharged. So, all right. So let's, if I can get this going, start to look at this problem a little bit. So in this particular problem, what is the system?
Everything inside the case?
Yeah, that's right. So it's really our laptop, right? Including the battery. And what's the surroundings?
The air in the suitcase.
All right, so we have the air in the suitcase. Anybody else?
The suitcase itself?
All right, so we have the suitcase itself. Anybody else?
Everything else that's not the laptop.
Yeah, everything that's not the laptop, right? Everything. So you could say that that's the case. Now, it is really interesting somebody brought up the air, because we didn't say anything about the air. So in this problem, we're going to have to assume that the only thing inside of the briefcase is the laptop. The real life answer to this would be that there really isn't that much air in the case itself, right? The overall mass of air is really, really low compared to the mass of the laptop. And so it would have a negligible influence on the behavior. So if we're going to have this just be an insulated laptop, including the battery, right? So we would kind of draw our system, right? This thing is well insulated, and this is our laptop. and that thing is the battery, okay? So we have a closed system, right? So we're gonna apply this equation up here, right? That delta U is equal to Q plus W. And so when you're solving problems like this on a closed system, really what we have to figure out first is what terms in this equation we have to consider. So let's just take those one at a time. So is the internal energy of the system going to change? Anybody? All right, so I'll ask it a slightly different way.
I
So,
would say no.
okay, so we have a no. So when I wrote this before, right, so delta U was equal to what?
Number of moles times the integral from T1 to T2 of the specific heat on delta time.
Yeah, not delta time, right? DT, the change in the temperature, right? Not time. But right, we have this integral from T1 to T2. So is the temperature going to change in this problem?
Yes.
Okay,
Yes.
so then is the internal energy going to change?
Yes, because the temperature changes.
Yep, that's right. So absolutely. All right, so we're going to have to consider the change in the internal energy. So what about Q? Is there any?
Q,
Oh, go ahead.
Is it PDV?
No, so
No.
no. So when in the past we've done this where work was minus PDV, but to figure out Q, what we have to do is ask ourselves, is any heat, right? We've defined the system as the laptop and the battery. So is any heat being transferred between the system and the surroundings?
No, because of the insulation.
That's right. So this thing is completely well insulated. So that is equal to 0. So what about work? Is there work that's going to be done?
Yes.
That's correct, right? And we know there has to be work done because the temperature is going to change. So then here's the question for you guys. What is the work that's being done? Because you're right, work is done.
Is it the heat transfer from the shoot?
From the battery to the
swatch.
laptop.
Yeah.
So here's where the discussion about a problem like this gets a little bit tricky, because your first instinct was to talk about heat transfer, right? But we already said the heat transfer was equal to 0. Now, what's going to happen is that the battery is going to apply current in your computer, right? And so it's going to keep the screen on, it's going to keep the hard drive running, all of that stuff. And that is essentially electrical work that's being done. And we could have drawn the boundary differently, right? We actually could have drawn the boundary as being the laptop, and then the battery could have been the surroundings, and then the energy balance around the battery would have just been like Q equals W, and then, you know, we could have treated the problem slightly differently. But here, where we define the problem as the laptop and the battery, we have this work term, and it's just the electrical work that's being done, right? So we have those two terms to consider. So we know that delta U is equal to the work that's done. And so that brings us to how much work would be done if the battery completely discharged. And we're given that in the problem. So we're told that the battery operates at, or has a voltage of 11.1 volts and 56 watt hours. So if you remember this, right, watt is a joule per second, right, times hours. So that's joules, hours over seconds. We'll end up correcting the units for that. So if you get the watt hour rating of a battery, that is a direct measure of the number of joules that are inside of that system. So we know then that the work that could be done by this battery is equal to 56 watt hours. And like we just said, that's equal to 56 joules per second times hours. And then we know there's 3,600, not equal, sorry guys, that we know then there's 3,600 seconds in an hour. And so we know that the work that's done, if we start with a completely charged battery, it goes completely to the discharged state, is 201,600 joules. And now we're given the heat capacity of the laptop in kilojoules per kilogram degree C. So I'll also convert this to kilojoules, right? So we know that there's 1 kilojoule in 1,000 joules, and that's 201.6 kilojoules. So that's the amount of work that the laptop is going to do. And so we know from this equation up here, right, that the work is equal to delta U. So we know that, 201.6 kilojoules is then equal to, in this case, we have the integral, or we have the heat capacity based on the mass, right, not the number of moles. And so that is a very reasonably easy substitution, right? And it's just m times the integral from T1 to T2 of CVDT, right, where the units for the heat capacity are equal to, are given in mass. Also, and I'll probably be able to show this before the end of lecture today, if not, I'll do it next time, that the heat capacity of a solid is the same whether you have constant pressure or constant volume. So we actually don't have to put the CV. So it's just the heat capacity times dt. I'll leave it there just because that's something you might be a little bit more comfortable with right now. But we're given a constant heat capacity, and so that just means that this is equal to mCV delta T. So we know the mass, right? We know the heat capacity, and so the only unknown here is the change in the temperature. So delta T is going to equal 201.6 kilojoules divided by 2.3 kilograms times the heat capacity, which is 0.8 kilojoules per kilogram degree C. And if we just want to take a look at the units for a second, right, kilojoules cancel, kilograms cancel, and we have 1 over Celsius, which is just Celsius. So then we can calculate the change in the temperature is equal to 110 degrees C. And in the past, what we've done is assume that room temperature was about 20 degrees C. So the actual temperature is then, T initial plus delta T, which then we'll say that that's 20 degrees C plus 110 degrees C. And so our final temperature is 130 degrees Celsius. So what do you guys think about that?
That was pretty simple. I felt pretty comfortable with that.
All right, that's good. What do you guys think about the temperature that we got?
It's hot.
Seems
Yeah.
a little.
Yeah, it's hot.
To be honest, I don't know. Well, actually, I've probably had a computer run that hot once, but that seems a little hot.
Yeah. It's, well, so I know one time that this happened to me. I reached into the bag and the laptop was at least 60 or 70 degrees C. And, this is one of those times where maybe it's a good thing that my briefcase isn't perfectly well insulated. And I don't know if you guys want a real world comparison for what 60 degrees C is. That's how hot a hairdryer is. So almost every hairdryer is designed for the heat to come out at 60 degrees C. And I'll tell you the story some point in the future of how I actually know that. And I've had to measure that before for work at a national lab, which was funny. But yeah, I mean, this is hot, right? It would burn your hands. So, all right, everybody seems reasonably comfortable with this one, which is good. All right, so then let's move on. Let's move on to the next problem. All right, so this time we're going to pick on electrical work or an electrical device again, but this time it's a hand mixer. So we're baking, and we're baking cookies. And so we're told that this electric hand mixer draws 1.5 amps at 110 volts. And the hand mixer is used to mix 1 kilogram of cookie dough for 5 minutes. After mixing, the temperature of the cookie dough has increased by 5 degrees C. If the heat capacity of the dough is 4.2 kilojoules per kilogram Kelvin, what fraction of the electrical energy used by the mixer is converted to internal energy of the dough? And then we'll talk about what happens to the rest of that. Okay, so we're back to sort of the same question that we started the previous problem with. So in this case, what is the system?
Would be the cookie dough.
All right, so we have one proposal that it's the cookie dough. All right, that's how I draw cookie dough. Is that okay? Anybody else?
What about the cookie dough and the mixer?
All right, so now we have the cookie dough. Oh, now I've pigeonholed myself. I have to draw a hand mixer. This is not going to go well. There we go. Magic. Okay, so now we have a second proposal, which is the hand mixer plus the cookie dough. Anybody else? All
Would it
right,
include
so-
the bowl as well?
Okay. I mean, we always could include the bowl. Actually, this is sort of an interesting question on where you draw the boundary, because you're not told anything about the bowl, which is actually somewhat interesting. So we could possibly include the bowl if we knew something else about it. Anybody else? Anybody have a preference? All right, my preference is to draw the boundary here to include the hand mixer. The reason that I want to do that is because the only thing that then comes sort of in here, for lack of a better word, is the power, right? The power outlet, right? This is going to go to the wall. And so the plug is now part of the surroundings, which to me makes the problem make a little bit more sense. And for us, we have the same equation that we had before to consider. So delta U is equal to Q plus W. And if we look at this problem, right, so we know that because the temperature changes, right, that delta U is going to change, just like the last problem. We know that we're going to have some work done, right, because these things are going to be spinning. You have current that's coming inside of the system. We don't know anything really about heat, although you're not told to assume that it's perfectly insulated. And in fact, the second part of this question, to determine the fate of the remainder of the energy, might lead you to believe that these two quantities aren't going to be equal to each other, right? That the work and the heat aren't going to be the same. So let's look at least these two terms that we know that we're going to need right away. So let's start with work. So work, here I'm going to change the color. So the work here is just power times time, right? We're going to apply some power. And here actually, because P for us is usually pressure, I'll actually write out power times time. And in an electric circuit, power is just current times voltage times time. And so we know then that the current here is 1.5 amps. We know that we're operating at 110 volts. And we're told that we're going to mix the cookie dough for 5 minutes. And so that's 300 seconds. And I just converted that right away because we know an amp is coulombs per second times volts times seconds. And so the seconds will cancel. That gives us Coulomb volts, which is joules. And so then the work is equal to then 49,500 joules. Okay. All right, so that's good. We have the work. So now let's look at the internal energy. So just like before, we have solid, we have the heat capacity based on the mass. The heat capacity is equal to a constant. So we have mCv delta T again, except this time we have 1 kilogram. The heat capacity is 4.2 kilojoules per kilogram Kelvin. And we know that the temperature of the dough increased by 5 degrees. So delta T is also 5 Kelvin. And so then delta U is equal to 21,000 joules. So if we do a very simple, if we take our energy balance that we had above, we actually can then calculate the amount of heat that is evolved, right? So that's delta U minus W, which equals 21,000 joules minus 49,500 joules. And so we find that heat, or Q, is equal to minus 28,500 joules. And so remember, our sign here is negative, so that means that the system is giving off heat. So some of the energy or some of the work increased the temperature, some of it released as heat. Now, where did that heat go is a really interesting thought experiment. So one thing that you could say is that, you know, maybe the dough is not perfectly well insulated. So you lose some to the bowl, you lose some to the surrounding air, right? That's entirely possible, that if you had measured the temperature of the bowl, you could have accounted for more of it, etc. The other interesting thing to note is that this thing, and this is why drawing the boundary where I did is really important, I think, for this problem, is that when you have an electronic device or any device, it doesn't operate at 100% efficiency. And so if you've ever used a hand mixer, right, you touch it when you're done, right, mixing whatever it was, and the mixer is definitely hotter than the cookie dough, which actually tells you that you're probably not converting all of this electrical energy or the work that you're doing into mechanical work down here. So if you draw the boundary here, you get to take all of the electrical work into consideration, and then you just say, okay, well, we just know it became heat. I don't care if it was inefficiencies inside of the hand mixer, or if we did heat the dough up more and it got lost to the bowl, it doesn't matter, because that's all part of the surroundings, right? That's not particularly important. But if you were to think about this, and let's say that it's the fact that all of the electrical energy is not becoming mechanical motion in the dough, and you wanted to say it was the efficiency of the hand mixer itself, you could actually calculate that, because you could say that the efficiency might be equal to the change in the I guess I'm trying to think of a really good way to do this. But in this case, maybe our efficiency would be the amount of energy that you added to the dough, which would be the 21,000 joules, divided by the total work that was done, which was 49,500, and everything else would be heat that you just lost. So anyway, let's not dig too far down that rabbit hole. But I wanted you guys in these first two example problems to just get a feeling for not just working with gases and PVT type relationships, but also to get a little bit of experience of very simple implementations of the first law with a type of work we won't talk about a lot, too many more times this semester, which is electrical work. So are these okay to you guys?
I mean, they seem pretty simple when you're going through and explaining them.
Yeah, we'll see. When you guys go back and either rewatch the video or you go through your notes, that's also what office hours are for. So, you know, if you guys have questions, please feel free to reach out and ask. Okay, so I said that these first two examples were meant to give you a little bit of experience with solid components and with electrical work and energy and that kind of stuff. So let's then take a step back and do something that we're a little bit more familiar with, and that's the behavior of gases. Okay, and what I'd really like to do is to explain to you guys really what the origin of the heat capacity is for a gas. And we're going to focus on an ideal gas. And if I really wanted to be more explicit about this, we're going to talk about a monatomic ideal gas. And since I'm going to do a derivation for a few minutes, let's go back and get full screen here. Okay, and of course, by a monatomic ideal gas, right? Monatomic is one atom. So we're talking like noble gases like argon, helium, you know, etc. And the reason that I like starting with those types of gases are that they're very, very simple, right? They can essentially be treated as hard spheres. And so for us to sort of wrap our brain around that, we have hard spheres, and because we're talking about ideal gases, we have no interaction between molecules. So that means that we have no potential energy change between molecules. So everything that we have to think about is essentially just accounting for the kinetic energy of these hard spheres, which you guys have done in physics before. We're going to do it you know, slightly differently. And to do that, right, I said we're going to say that these are hard spheres. We're going to assume that since it's an ideal gas, if molecules hit themselves or hit each other or a boundary, you probably shouldn't hit yourself. That's not good for your health. If you hit a boundary or another molecule, that you have elastic collisions, which in this case means that the velocity will be the same when you hit the boundary or something else, and that molecules don't occupy volume, although I won't really dig into that too much here. So if we have this, we have hard spheres moving around, the easiest system to really try to wrap our heads around is just a box, right? So we're going to have a box, right? And of course, right, boxes have 3 dimensions. And if I really want to do this, you know, somewhat properly, let's think about this as 3 axes, okay? And we're going to call this the y direction. We'll call this the z direction. We're going to call this the x direction, okay? And we're going to take one hard sphere that's on this wall, all the way on the left-hand side of the box. And we're going to see what happens when this thing moves in the x direction until it reaches this boundary over here, okay? So all we're going to do is think about what happens when this moves all the way to here and then it bounces back in this direction, okay? And then we're going to use that to generalize what happens for all the gases. And I want to start by first talking about pressure. So we know that inside of this box, right, the pressure that is exerted on the boundary is just the force divided by the area, right? Now, when you guys took physics, the force on a wall could also be related by the change in the momentum over time. So you guys may or may not remember that that is dmv, where v here is the velocity. I know we've used v in terms of volume. So maybe I'll do this. I'll just write a little line over the top of it to keep velocities distinct from volumes. Or if we look at it for some finite amount of time, we could actually say that the force is equal to the change in mass times velocity over delta t, okay? And remember, we're thinking about this time when our hard sphere goes all the way to this boundary and then comes all the way back. And the act of that happening for an elastic collision, if we think about then this change in m times v, right, that's equal to, if we're looking at just the particle moving in one direction, so then that is m times vx minus, and if the collision's elastic, the velocity coming back left here is also vx, but it's facing the opposite direction. So that's minus m times vx. So this delta mv term is just equal to 2 times m times vx, okay? And we can use this fact that the velocity is the same in both directions to also understand a little bit more about delta t. So we know then that the velocity that must have been covered, right, or the velocity of x, then equals 2 times L over delta t, right? Because this time that we had was this bouncing here and then bouncing all the way back. And that would be the time that it took for that to happen, and it traversed 2 lengths during that time. So then delta t just equals 2 times L divided by Vx. So we can use this and actually find the force, right, using this equation that's exerted by this one argon molecule, right? So the force then is equal to 2 times m Vx divided by 2L divided by Vx, or the force is equal to m Vx squared divided by the length. And remember, we started this by wanting to understand pressure. And so if that's the force, well, we have force over area is equal to pressure, right? Pressure equals force over area. And so that just equals m Vx squared over L divided by the area, and the area of this box is just this length squared. So finally, we have the pressure exerted by one molecule is equal to m Vx squared divided by L cubed, okay? So now what we have to do is we understand what the pressure is that's exerted by just one molecule, but our systems don't contain just one molecule. So now we have to sum over every molecule that's in the box. So our total pressure is just equal to the sum of the pressure that is exerted by each molecule. So then the pressure then is equal to the sum from the first molecule to the last, where I'm going to define this as N times Na. And here N is equal to moles. And Na, just like in chemistry, is Avogadro's number. And so that gets us to sum over every molecule in the box, and that is just M times V X of that species squared divided by L cubed. And that is just equal to, if you think about it, the mass of each individual molecule times N times Na times the average velocity in the x direction squared divided by L cubed. And I know derivations aren't a lot of fun, but trust me, we'll get somewhere we want to be relatively soon. All right. And where these two equations really differ is that initially here, I only had this thing moving exactly in the x direction. Now here, I'm allowing things to move in any direction that they want, where now I have some average velocity in x, but I'm still finding the pressure exerted on that boundary. So if we want to relate that to just the average velocity of any gas, well, we know that the average velocity, the average linear velocity squared is just equal to the x velocity squared, right, plus the average velocity in the y direction squared plus the average velocity in the z direction squared. And if we can assume that motion is totally random, well, these three should be equal to each other, right? If there's nothing else that influences the, if nothing else is influencing the motion, these three should be equal to each other. And if that's the case, we can actually just say that the average velocity squared is just equal to 3 times the average velocity moving in the x direction squared, right? Because y and z are just equal to that number. And if we rearrange this a little bit, we now have that the pressure equals m times Avogadro's number times the number of moles times the average velocity of something inside of this box squared over 3 times L cubed. And I flipped these two when I did this on purpose because we know that the mass times Avogadro's number is just equal to the molecular weight. And in our box, L cubed is equal to the volume. So if I substitute those into here, what we find is that we have 3 times P times V, right? Because L cubed just became V, equals N times the molecular weight times the average velocity squared, okay? And now what we're going to do is apply the ideal gas law. So PV equals nRT. So that means that 3 nRT equals N times the molecular weight times the average velocity squared. And so these n's cancel, and we're simply going to solve for the average velocity. So the average velocity of one of these molecules is equal to the square root of 3RT divided by the molecular weight. And you guys are thinking, how in the world is this related to heat capacity? Okay, so here's where we make the link, that the heat capacity of a monatomic ideal gas is only kinetic energy, right? We sort of mentioned that before. So let's find the kinetic energy of this one molecule, right? Knowing these things, right? And so, or of the average molecule, right? Not this one. So the average kinetic energy is just equal to 1/2 times m, right? Times V average squared. And so that equals 1/2 times mass times just 3RT divided by the molecular weight. And that then equals 3/2 times RT divided by the total number, right? The mass over the molecular weight is, again, just Avogadro's number. So then if we sum over all the molecules, right? So we're going to say that the internal energy is the sum of the kinetic energy for everything inside the box. Well, if we sum over all of those species again, just like we did before, right? Where from I equals 1 to n times Na, we're going to sum all those kinetic energies. And we get that that's 3/2 times RT over Na, which we just had, times, remember, just like we had above, this is just the number of moles times Avogadro's number. And those are going to cancel. And that means that the internal energy here is then just equal to 3/2 times N RT. And if you remember that we had an expression for the internal energy, so I'm going to take the differential of U, and so du then equals, if you think about everything in this box, right, these are all constants. So du equals 3/2 or N times 3/2 times R dt. And remember that delta U for an ideal gas was equal to N times the integral from T1 to T2 of CV dt. And so if we just look at these by comparison, we actually have derived that the constant volume heat capacity for a monatomic ideal gas is equal to 3/2 times R. And we're going to use this a lot over the course of the semester in solving problems. Okay. And we actually will solve the first one right now. So let me get this back up here. All right, so our next example problem that we're going to solve says that 4 kilograms of argon, which of course is a monatomic ideal gas, is placed inside of a well-insulated, rigid, closed oven at room temperature and atmospheric pressure. How long in minutes should the oven be turned on to raise the final temperature of the argon to 500 degrees C if the oven heater is rated at 400 watts? So now we're going to do something we sort of did earlier with something that we did earlier. So we know that we have this rigid closed box. So if we're going to write the energy balance here, so then du is equal to dq plus dw. So one of the things that we really do need to think about in a problem like this is, what is the system? So my preference here in defining the system is just to let the system be the gas inside of the oven. And so that way we don't have to worry about, we actually don't have to worry about a whole lot other than the change in the internal energy and then the heat that gets added from the oven. So if that's true, and we have a rigid box, right, where the volume doesn't change, right? We know that V is equal to a constant. And we're just going to treat the oven like it gives us heat. That means that there is no work that's done in this particular problem. So our answer here is just that dq is equal to dw, or at least the solution to our energy balance. And so now we have enough information to calculate these quantities, right? So the first thing I want to look at is the change in the internal energy, because we know that 4 kilograms of argon is going to go into this oven at 20 degrees C, and we want to raise the temperature to 500 degrees C. So we want to know how many joules it's going to take to do that, right? Or how much the internal energy increases. So if we're going to do that, then delta U is then equal to N times the integral of CV dt from T1 to T2. Now, here, we're going to use the thing that we just learned, is that CV, we're going to assume it's equal to a constant, and it's equal to 3/2 R. So then the change in the internal energy just equals N times CV delta T, okay? And if we want to calculate the number of moles of argon, right? Because R, the units of R are things like joules per mole Kelvin. So we kind of do need to do this in joules. Well, we know we have 4 kilograms of argon, right? So N is 4 kilograms divided by the molecular weight, which is 40 grams per mole. Then we'll convert from grams to kilograms. We know we have 1,000 grams per kilogram. So N is equal to 100 moles, right? So delta U equals 100 moles times 3/2 times R times delta T, okay? All right, so there's delta U. And now what about Q? Well, the amount of heat that we have to add that's going to come from the oven is the same thing that we had before, although since last time the heat source was part of the system, we called it work. But we're still interested in power times time. So if delta U is just equal to Q, so we have power times time equals our 100 moles times 3/2 R times delta T. And really what we're asked is how long do we need to heat this up? So the time is equal to 100 moles times 3/2 times 8.314 joules per mole Kelvin times delta T, which is 480 Kelvin from the problem, divided by our power, which was 400 watts, which is just 400 joules per second. And if we look at the units here, right, so moles should cancel, joules cancel, and Kelvin will cancel. And we know then that the time is equal to 15,000 seconds, which equals 25 minutes. Okay? We also then could answer the second question here about what the final pressure of the gas would be. And now we know the oven has constant volume, there's a constant number of moles. So P1 V1 equals nRT1. And then if we divide, right, P2 V2 over nRT2, well, we know that the volume's the same, the moles don't change, and R is not going to change. So P2 just equals P1 times T2 over T1, which equals 1 atmosphere. And then we're going to multiply by, remember, the ratio of the absolute temperatures, not the temperatures in degrees C. So 500 degrees C is 773.15 Kelvin, divided by the initial temperature, which is 293.15 Kelvin. And so that means that the second pressure then is 2.6 atmospheres.